Hello, I'm Martin Looker. Welcome to this Silicon Labs video where we'll be taking a quick look at a new GPS asset tracking application that makes use of the Silicon Labs SiWG917 Wi-Fi chip. The application transmits data over Wi-Fi to the Azure Cloud. A locally running dashboard captures the Azure data to a MongoDB database and displays it in a browser. Historical data from the GPS and sensors can be downloaded to an Excel file, along with a GPX file that allows the GPS trace to be displayed in mapping software. In addition to the GPS board for location, there is also an inertial measurement unit sensor board and a temperature and humidity sensor board. All three of these boards are from SparkFun. Links to the resources and hardware shown can be found in the video description. This example was originally created by eInfoChips, an Arrow company, who provide consulting, design, development, and testing services together with expertise in Silicon Labs wireless technologies. If you need any of these to assist in the development of your project, please reach out to them. There are lots of steps to set up this example, so I won't be showing them all. But where I do skip over steps, I'll refer you to the step-by-step instructions. I'll begin with the Wi-Fi example applications available on GitHub. This repository contains the example Wi-Fi asset tracking application for the SiWG917. Currently, this is the only example, but more will be added in the future. You will need to clone or download the repository so the files for the dashboard component of the application are on your local PC. I have already downloaded to my local PC. If you click through to the Asset Tracking Example README in the System Overview section, you will find links to the READMEs that cover how to configure the Azure Cloud dashboard and the project for the 917 application. The Wi-Fi applications repository can be integrated into Simplicity Studio, allowing the project to be created with just a few clicks. You can find instructions for this in the main repository README. The asset tracking example makes use of some third-party hardware drivers for the external sensor boards. This extension can also be installed into Simplicity Studio by following the instructions. This makes a set of simple driver applications available for the hardware boards, but more importantly, also exposes them as software components in the IDE, which can be easily added to applications to accelerate your project development. Both of these are pre-installed on the laptop I'm using today. Now I have everything needed from GitHub, I'll provide an overview of setting up the Azure Cloud part of the application. Step-by-step instructions for setting up the Azure entities are in the GitHub READMEs. This is quite an involved process, so I'm going to use a setup I already have in place. As you step through this process, you'll need to keep a copy of some IDs and credentials to use later when setting up the dashboard and the firmware. With Azure set up, we can turn to the dashboard next. The files for this are included in the GitHub download. Once again, step-by-step instructions are in a README on GitHub, and I've gone through most of these already. You'll need to install Node.js and also MongoDB. The dashboard is divided into a backend which obtains data from Azure and writes it to a database, and a front-end which displays the data in a browser. For both of these, you will need to construct a .env file containing IDs and credentials copied while setting up the Azure Cloud. To run the dashboard backend, you'll need to open a command window in the backend folder. Before you run for the first time, you will need to issue npm install command, which will install or update dependencies. Then, entering npm run start will begin the backend, which will continue to output diagnostics whilst it runs. The dashboard front end is similar. Open a second command window in the front end folder and before the first run use npm install again. The front end can then be started by issuing the npm run dev command. The dashboard can be opened in a browser by typing O, then pressing enter. You may need to log into the dashboard using a Microsoft account. As the device is not yet running, the data in fields will indicate no data available. Now, I'll complete the final part and create the firmware project in Simplicity Studio. I've already installed the Wi-Fi applications and third-party hardware drivers from GitHub into Simplicity Studio, so it is ready to create the application project. It begins by connecting the ProKit with the SiWG917 radio board via USB. Then go into the launcher perspective if you're not already there, and select the board in the Debug Adapters panel. Select the Example Projects and Demos tab, and then search for Asset Tracking. In the Asset Tracking box, click the Create button to begin creating the example. In the New Project Wizard window, click the Finish button to complete the project setup. Simplicity Studio will then switch to the IDE perspective, and the new project is created in the Project Explorer panel. Next, we need to configure the Wi-Fi access point the device will connect to in order to send its data to Azure. To do this, open the slnet defaultvalues.h file in the config folder within the project. Enter the SSID to connect to in the default Wi-Fi client profile SSID define, and also enter the passcode for the access point in the default Wi-Fi client credential define. You can then save the file and close. We also need to enter Azure IDs and credentials used by the project. To do this, open the SL Wi-Fi Asset Tracking Demo config.h file in the main project folder. Then enter the following hash defines using data collected while setting up Azure: the demo config IoT Hub hostname, the demo config device ID define, and finally the demo config device symmetric key. Save the file and close again. With the header files updated, we can compile and flash the application. Start by selecting the top-level project in the Project Explorer panel. Click the Build button on the toolbar, and the build progress will be displayed in the Console tab. Once compiled, in the Project Explorer, open the Binaries folder. Right-click the .s37 file and select Flash to Device. In the Flash Programmer, click the Erase button to ensure a clean device, and then click the Program button to program the firmware. You can then use the Close button to exit the Flash Programmer. The LCD on the ProKit board will then display progress as the application starts. With everything in place, we can now see the application operating. The dashboard displays the current and some historical values in the forms of graphs collected from the sensors. Moving and rotating the inertial sensor board will update the inertia graphs. Covering the temperature and humidity sensor will alter those readings. Covering the Wi-Fi antenna will affect the Wi-Fi RSSI. Copying the coordinates into Google Maps will show the location. Historical data can be downloaded using the download buttons. Here you can see the Excel spreadsheet I downloaded that contains the various sensor readings. The GPX download can be overlaid onto a map in mapping software or on a website, and you can see the locations where the device has been. You can also view and monitor the data throughput within Azure. Administrators of the Azure subscription can enter into the event hubs and select which node to inspect. You can monitor activity in real time, viewing the incoming messages, outgoing messages, captured messages, and a timeline of events. This example, while complex, illustrates a method to store, transfer, and display data over Wi-Fi. The sensors that have been used in this application could be swapped out for different ones depending on your application needs. Similarly, if you prefer other solutions than Azure and MongoDB, you could also replace those with your preference. The resources used in this video can be found in the video description. Thanks for watching.